Today we will look at stoichiometry, and stoichiometry is a big concept in chemistry where we use the mole and mole ratios to look at balanced equations and to relate the reactants in the products. So what we're going to be focusing on today is using those mole ratios to convert between reactants and products. So stoichiometry, aside from being a fun word, is just representing the numerical relationship between chemical quantities in a balanced chemical equation. And so this allows scientists to predict the amount of product that should be formed or the amount of reactant that would be needed. And it allows them to then carry out the reaction to produce as much as they want. It also allows us to look at how efficient a reaction is and how much yield we're getting. And so with all of that, we're able to just do a lot of different kind of functional things and product related things in chemistry. So with stoichiometry, we need to have a balanced chemical equation because you need to be able to identify the mole to mole ratio with the products and the reactants. So one example that we normally use whenever we talk about stoichiometry is baking. So baking is a type of chemistry. And whenever we're looking at baking, we have a recipe, which is essentially our reactants, and then we get our products, which hopefully are yummy at the end. But what we find is that we can relate what we have as our reactants and our products. So if these are our reactants, flour, eggs, and baking powder, how does that relate to the number of pancakes that we get? And so if we're looking at that, then we could say for every 1 cup of flour, we have 2 eggs, we have half a teaspoon of baking powder, and we have 5 pancakes, which is how much we would be produced. And so these would be our example of our mole ratios whenever we're looking at baking. So obviously this is important to know because if you only have half a cup of flour, well then you know that you don't have enough to get these 5 pancakes. And so then you would need to either go to the store or you would need to adjust your recipe. So some applications of this. So if we wanted to make 20 pancakes, how could we use all of these relationships to figure out how many eggs that we need? Well, okay, so we have 5 pancakes and we want 20, so we want 4 times as many. So you could think just logically, okay, well that means that I would need 8 eggs. Or we could set it up the chemistry math way where we would say, okay, well we want 20 pancakes. If for every 5 pancakes we need 2 eggs, then this tells us that we need 8 total eggs in order to do this reaction. So how does this relate to chemistry? Again, balanced chemical equations are going to be necessary to identify multiple ratios in order to help us to relate reactants and products. And this relates to baking because it allows us to identify how much we need, how many reactants we need, and it allows us to know how many products we're going to get. So if we were looking at this equation here and we wanted to determine our mole ratios, our mole ratio here for our balanced chemical equation would be that for every 3 moles of hydrogen, we would need 1 mole of N2, and we would then produce 2 moles of NH3. And so these would be our mole ratios. We could set these up as conversion factors and help us to solve some problems. So let's do that. So if we have 3 moles of nitrogen and then more than enough hydrogen, so that's not going to limit anything, how much NH3 could we make? So we would set it up in this manner. We would say that we have 3 moles of N2, and for every 1 mole of N2, we produce 2 moles of NH3. So 3 times 2, so we would have 6 moles of NH3 would be produced if we have 3 moles of N2 and more than enough hydrogen. Okay, notice our moles cancel out and we're left with moles of ammonia. So whenever we're doing these, this is just using our relationships and we're just looking at balanced chemical equations now, and instead of relating them as molecules, we're just saying that we have moles of this, or just relating the quantity and making it bigger essentially. Okay, so let's go ahead and do another example. So if we look at our mole ratios for this example, we would have 2 moles of sodium for every 1 mole of chlorine for every 2 moles of NaCl. So if we're looking at this, if we have 3.4 moles of Cl2, now which relationship would we put in here? Well, we want to look at how chlorine and sodium chloride are related. So we have 1 mole of Cl2 for every 2 moles of NaCl. And so if we multiply these, we got rid of the moles here. And so now we have 6.8 moles of NaCl that would be produced in this reaction. Okay, let's go ahead and do another example. Okay, so if we are looking at the formation of water, so again, our mole ratios or our relationships would be that 1 mole of O2 for every 2 moles of H2 for every 2 moles of H2O. So if we start out with 24.6 moles of oxygen and we want to know how much water we have, then we would say that 1 mole of oxygen gives us 2 moles of H2O. We'll go ahead and multiply that by 2, and we get that we have 49.2 moles of water that would be formed if we started with 24.6 moles of oxygen. Let's look at one more thing together. So if we are looking at an example of a combustion reaction here, where we have methane, which is CH4 undergoing combustion, look at the figures below. So if this figure on the left-hand side here represents oxygen, which is O2, so each of these is O2. Okay, so in this example, we have 4 O2. So it's asking which of these CH4 examples represents the amount of CH4 that we would have. So we could solve it this way. We could say that we have 4 O2, 4 moles of O2, and that for every 2 moles of O2, we have 1 mole of CH4. And so that would leave us with 2 moles of CH4. And so the picture that would represent that would be picture A, which represents 2 moles of CH4, or even you could say 2 molecules of CH4. All right, so that sums up the initial part of stoichiometry, where we have mole ratios and how we used a balanced equation to relate our reactants and our products.